Everyone, welcome back to my video, and today I'm going to presenting um, my work on my subject, which is mathematical logic for meetings 13 and 14, and my lecturer is Iip Permana STMT. And yeah, let's go video. In this video I will explain to you um, meeting 13 mathematical induction and meeting 14, which is set. Mathematical induction is used to test a conjecture from a process that appears repeatedly and has a certain pattern. For example, in the US, there are 1 cent and 5 cent denominations. Suppose a 3 cents denomination is made, then every large price equal to X cents can be represented by 3 cents on N or 5 cents. Formally, for all N greater than 8, N can be represented by 3N or 5. And yeah, these are the simulation 3 and 5 for N greater than 8, as you can see from this picture or table. And yeah, the secret is to observe that if K is obtained with at least one 5 cent coin, then K plus 1 is obtained by replacing the previous 5 cent coin with two 3 cent coin. From that, we get a conclusion that to show that Pn is true for all integers n greater than 8. Number 1 is show that Px is true, and number 2 is show that the truth of Pk plus 1 is obtained from the truth of Pk. Formally, ordinary mathematical induction can be written as follows. And yeah, let Pn be a property that is defined for integers n, and let A be a fixed and integer. Suppose the following two statements are true, and we get two statements. One, Pa is true, and for integers k greater than a, if pk is true, then pk plus 1 is true. Then the statement for all integers n greater than a, pn is true. Then yeah, we have example for the mathematical induction. Here is the example question. Prove it by ordinary mathematical induction if n is a natural number. Yeah. Then 1 plus 3, 1 plus 2 plus 3, and plus n equal to n times n plus 1 per 2. Yeah, these are step by step how we, yeah, for the basic step, which is show that p1 is true, is basically this. We implemented this step number 1 in this, and yeah, we substitute number 1 to the formula, which is the uh, which is 1, which is true, and the induction step is the statement number 2 right here. Yeah, we substitute the k plus 1 to the formula, and we will get the answer, which is k plus 1 and k plus 2 per 2. Yeah. Then we have the second type of mathematical induction, which is strong mathematical induction. Is proof of strong mathematical induction also involves two stages, namely the basis stage and the induction stage, like the regular mathematical induction. The difference is that the basis stage can have several initial value proofs, and in the induction stage, the truth of a predicate Pn is assumed not only for the one value, but for all values up to k, so that Pk plus 1 can be proven true. For that, we can get the conclusion that to show that for R and Pn is true, the basic step is that to prove that P1, P2, P3, and Pn are true. The induction stage is to show that The truth of pk plus 1 is obtained from the truth of the basic stage. Formally, strong mathematical induction can be written as follows. Let Pn be a property that is defined for integers n, and let a and b be fixed integer with a less than b. Suppose the following two statements are true: pa plus 1, and bb are all true. That are the basic step. And number 2, if for any integers k greater than b, if pi is true for all integers I from a through k, then pk plus 1 is true, then that is the inductive step. Then the statement for all integers n greater than a, pn is true. The supposition that pi is true for all integers I from a through k is called the inductive hypothesis. Another way to state the inductive hypothesis is to say that pa plus 1, and pk are all true. Yeah, we have the example of the strong mathematical induction, which is proof that the function Pn equal n is divisible by prime numbers. Yeah, first we have to find the basic stage, which is test P2 equal to 2 is divisible by prime numbers, namely 1 and 2. And then the induction stage show that for all integers k greater than 2, if pi is true for all integers I from 2 to k, then pk plus 1 is also true. Let k be any integer where k greater than 2, and let I be divisible by prime number for all series I from 2 to k. We must show that for k plus 1 is divisible by prime numbers. And then we have two cases of the question. Case 1 is k plus 1 is a prime number. In this case, k plus 1 is divisible by a prime number, namely itself. Case 2, k plus 1 is not a prime number. In this case, k plus 1 equal ab, where a and b are integers with a greater than 1, and a less than k plus 1, and b greater than b, and b less than k plus 1, and a greater than 2, and a less than k. By the induction hypothesis, a is divisible by a prime number p. In addition, since k plus 1 is ab, we know that k plus 1 is divisible by a. Since k plus 1 is divisible by a, and a is divisible by p, either transitively or by division, k plus 1 is divisible by the prime number p. So, whether the value of k plus 1 is a prime number or not, it will always be divisible by a prime number. Yeah, that's for my meetings 13, and now we will get to the meeting 14, which is set. Set is a collection of different objects that are not ordered. Objects in a set are called elements, members, or elements of the set. Set's notation is usually capitalized, which is like here, A, B, C, and X, Y, Z. And set member notation is usually lowercase, same but is low, same alphabet but is lowercase. For example, the notation X element A states that X is a member of the set A. The notation X is not element A states that X is not a member of the set A. The notation empty set, this called empty set, states the empty set which has no members. And then we have universal set and Venn diagram. Universal set is the entire set of objects being considered. The universal set is denoted by S or U. The example. The set S, X is element N, and X greater than 20 and X less than 45. Then the set S is 20, 21, 22, 23, and then we will get to 45. And then we have Venn diagram, graphical, which is graphical illustration of the relationships between members of the universal set. The example of the Venn diagram is, suppose there is a semester set as follows: S, X is element n, and X greater than 21, and X less than 33, and X element prime number. And we have A 21, 22, 23, 24, and 25, and B 26, 27, 28, 29, 30, and 31. Then we have the Venn diagram right here. Why is 23, 21, and 31 in the middle? Because we have right here the X element is prime number, and then the number one, like the number in right here is prime number. Yeah, and then we have similarities of sets and subsets. Sets are said to have similarities if they have the same element. The set of the same elements is denoted by A equal to B. The set of dissimilar elements is denoted by A is not equal to B. The set A is a subset of B if every element of the set A is also an element of the set B. The set A is a subset of B is denoted by A is subset of B, like here. The set B is a superset of the set A, like as we can see right here on the picture, where uh, in inside the set B we have the set A, uh, which is the set A is the subset of B, and it's also can be concluded as the set B is a superset of the set A. And yeah, then we have the cardinality of finite sets and equivalent of sets. A is said to be a finite set if contains exactly n elements for a non-negative integer n. N is said to be the cardinality of A, and A is denoted by these three symbols. Yeah, A is said to be an infinite set if A is not a finite set. Two sets A and B are said to be equivalent. These are the notation for equivalent, which is this symbol right here. And if their cardinalities are the same, if A and B are finite, then A equivalent B if A is equal to B. Then lastly, we have power set. If A is a set, then the power set of A is a set whose members are a subset of A. The power set of A is denoted by 2 to the power of A, WA, AW. Sorry, I mean YA. Yeah, YA. For the example question, I have three questions right here. Given the set A 1, 2, 3, answer the following question. Number 1, what is the power set of A? And number 2, determine the cardinality of the power set. Number 3 is 1 and 2 is subset of A. Justify your answer. And we have the answer on the next slide. The answer for the question number A, what is the power set of A? The power set of A denoted by 2 to the power of A is the set of subsets of A. So 2A, this right here is supposed to be this, yeah. I guess I forgot, yeah, I'm sorry. It's empty set 1, 2, 3, 1 and 2, 1 and 3, 2 and 3, and 1, 2, 3. And yeah, for the answer question number 2 is cardinality of the power set, which is the cardinality of the power set is given by 2 to the power of n, where n is the number of elements in the original set A. Since A has 3 elements, we get 2 to the power of A, which is 2 to the power of 3, and the answer is 8. Subset check for the question number 3. Is 1 and 2 subset of A? Yes, 1 and 2 is subset of A because all elements of 1 and 2 are also elements of A. This satisfies the definition of a subset where every element of the subset is contained in the original set. And yeah, And that's all for my presentation. Thanks for watching my video, and assalamualaikum warahmatullahi wabarakatuh.